In this lecture set, we'll be discussing the ANOVA analytical approach. For some context about where this approach fits in relationship to the other approaches we've discussed in class, recall this table. In the ANOVA analytical approach, we're going to be looking at categorical independent variables that align with dependent continuous variables. And when we analyze one of these situations, the analytical approach that we'll use for our inferential statistics is called broadly ANOVA. Now, I will mention here that you'll hear some other analytical approaches that can be used. Sometimes you'll hear of the z-test, which we've discussed previously in the Foundations of Inferential Statistics lecture. You'll also hear of the t-test, which can be used similarly while we used the z-test and referenced the z-test in comparison between a single group and a pre-existing hypothesis. You can also use those tests to compare two groups. ANOVA subsumes all of those, and I should maybe be more specific. When comparing two or more groups, ANOVA is appropriate. So broadly speaking, ANOVA subsumes the classic Z and T tests that sometimes you see used in the same context. That is, you can use ANOVA in that context as well, which is why we'll only be discussing the one analytical approach rather than several. I will also say that ANOVA and the t-test are statistically analogous. That is, they give you the same p-values. They give you, in terms of transformation, the same test statistic, though one is phrased as a t-test, one is phrased as an F distribution, but we can convert those two distributions, and after conversion, those are going to be the same test statistics. So within these, they really are the exact same thing. The only difference is that ANOVA is the more broad approach. So let's jump into what is ANOVA. ANOVA stands for Analysis of Variance, which is in some ways a bit of a misnomer. All inferential statistics are, in and of themselves, analyses of variance. But this test that we'll be discussing in this lecture set is considered the analysis of variance, not because it is the archetype of analyses of variance, but because that's the classic name associated with this test. Again, in some way, someone is working with statistics is always going to be working with variation. Virtually none of our statistical inferential tests run without variation, and thus all of our statistical inferential tests are themselves analyses of variability. So if you hear somebody talking about analysis of variance, you can, in your own mind, note that in a somewhat semantic way, that could be any inferential test, but note that they are talking about this test, this particular analysis of variance. And as we mentioned earlier, this is an extension of the z-test that we discussed in the Foundations of Inferential Statistics lecture. That test, which we only covered that one, and we kind of mentioned that the t-test could also be used. These those were used in the context of a single sample. As we extend that to comparing more samples, so we had, say, looking at comparing some level of patients in a hospital to a pre-existing value. The immediate extension, which still falls under the realm of the z-test, well, it's actually under both realms, is if we want to compare patient loads at two hospitals. And then as we want to compare three or more, then we dive into this ANOVA extension. So I get a bit of ahead of myself here, but when do we use ANOVA? Well, we use ANOVA when we have the continuous dependent variable, and then we want to compare that between multiple levels of a categorical independent variable. And again, we need two or more levels in the categorical independent variable to run the ANOVA analysis. Now, when I say two or more levels, recall that when I have a categorical independent variable, a factor, the levels are just the number of options. So what you can think of is comparing males versus females. Those are two levels within an independent variable called sex. You can think of comparing multiple races across, say, health outcomes. Each race would be a level of the categorical independent variable race. So in this case, we're dealing with a continuous dependent variable and a categorical independent variable with 2 or more levels. Now, what's interesting is you'll see the ANOVA used in a wide variety of observational designs, but observational designs often use things like correlation, they use regression, sometimes they use chi-squared, they use a lot of different things. However, for experimental designs, ANOVA or analogous procedures are often used. And take a moment to consider why. Even if we had a naturally continuous independent variable, we tend to design experiments to focus around particular values along that continuous spectrum. Consider, say, a test where we're looking at outcomes based on drug dosages. If we're creating an experiment, that is, we get to assign the dosage to a particular person, don't often do this when we assign a dosage of, say, the full dose, or 1.1 times the dose, or 1.02 times the dose, or 1.03 times the dose, etc. Typically, what we might do is half a dose, 3/4 of a dose, a full dose, but we wouldn't do all of the decimals in between. That is that what we're essentially doing is categorizing the dosage. We're taking a continuous variable. We are chunking participants into multiple levels of that continuous variable. And thus the appropriate analytical method or inappropriate analytical method is this analysis of variance. Now, I hesitate to mention this because I find it useful and interesting to understand why ANOVA is so often used in experiments, but we do also have to call out, and I don't want to confuse you, experiments are a study design. ANOVA is a statistical method. So though ANOVAs are often used within the context of experimental designs, again, because even if we had a continuous independent variable, we often treat it categorically, it doesn't mean that ANOVAs are the only analysis for experimental designs, or if you see an ANOVA, it's definitely an experiment. I say this to remind you the inference and study design contribute different things to that statistical story that we've discussed previously. Now, one other cool thing about ANOVA is that in addition to just testing more than 2 levels of a categorical independent variable, which is a previous limitation with Z and T, this also lets us test multiple independent variables at the same time. So when I say more than 2 levels, think instead of doing sex, I'm doing race, where I have multiple races, not just 2. That's multiple levels. And that was a cool enough contribution from ANOVA. What this bullet point is describing is that ANOVA can handle multiple variables. So I don't have to pick between sex and race. I can study both of them at the same time, and that's a pretty cool feature. Now, when we do this, if you include some variables that maybe you don't care about but want to make sure are controlled for, that's also a legitimate purpose of these additional variables. And the end conclusions of the interpretations that we make when we include multiple variables are after controlling for blank. So if we drop in a bunch of controls, say demographic factors, then we can make conclusions about the relationship between the independent variable and the dependent variable after controlling for those demographic factors. So why do we do this approach? And it's a bit interesting. So consider what we did previously in the foundations of inferential statistics. So we're not looking at chi-squared because chi-squared had a categorical outcome. So we're going back to the inferential statistic we talked about in this course, where we've looked at a continuous outcome. In this case, with groups, in this case, the z-test we talked about was a single group. We took a single group, calculated the mean, and compared it to the pre-existing mean. That is, we subtracted the 2 and tested if the difference was from a distribution with a mean of 0. We can do this with 2 groups in a really similar way. So previously we would subtract the null hypothesized mean from the mean. With two groups, we take one group and subtract the second group's mean from the first mean. Now, there's a little bit of complexity when calculating the standard error, but by and large, this is a very similar process to what we did previously. And in fact, in a pinch, you could probably just average the two standard errors together and get a relatively close estimate of what you're going to get. It's not, I'm not saying do that, but again, this to say, it's a very similar procedure in how we're approaching the test and how we're approaching the logic of what's going on behind it. So for an example of this, consider we're studying systolic blood pressure, males versus females. Subtract the means of these two levels. Remember, male and female are two levels of the factor sex. So we subtract the means of the two levels from one another. All right, so that's two groups. The issue is when we get to more than two groups, because while we can subtract males from females, if we have multiple races, and let's say we're studying a group with 6 different races that have been identified within our population, and we're trying to compare the average systolic blood pressure between them, it's difficult to identify exactly what we would do to get a test to see are any of the races different. Now, I want to take a second to acknowledge we could actually be clever about this and test every pair of variables or every pair of factor levels. This approach is actually called pairwise comparisons, and we'll even discuss that later in this lecture. Suffice it to say for now, if you did this, you would not get kind of an overall summative test on are there any differences among the races. You would only have pairwise comparisons to say there's a difference between A and B. Also, it increases our error rate. Consider that every test has the possibility of error. So when we do multiple tests, we add error because each one could be an error. So we increase the possibility of error with every additional test. This is true in general, actually. It's not just for this particular problem. If you ever see a report with lots of inferential statistics run, you should be pretty careful. The error rate overall that at least one of those is wrong is higher than the traditional 0.05 specified or whatever they ended up using, unless an analyst used a method to control for the error rate. Again, we'll talk more about this later in the lecture set, but that is something to be aware of. So in this case, again, it's difficult to think of because with two levels, we say we subtract one from the other and we test the difference between them. But with, say, 4 or 5 or 6, it's not really clear how we address this. The answer to how we do this is actually pretty clever. What we do is instead of looking at the difference, a subtraction problem, we look at the variation. And we look at it in a pretty clever way. What we do is we look at the group means and we assess variability, like a literal variance calculation, though it has a slightly different meaning in this context, but a literal variance calculation between the group means. The idea is that if there is variability between the group means, then there's differences, because if there's no variability, they're all the same. But if there is variability, then something must be different. So that's actually the cool contribution. That's the cool thing that ANOVA does. It's why it's called the analysis of variance, is we're analyzing the variance to see is the variance greater than 0. And again, if we have evidence for that, then we would determine that there's a difference in the groups. We don't know where that difference is, but there's some differences between the groups because there is variability among them. And so that's the idea behind ANOVA. Now, as with our previous tests, we can't just test for the difference, right? So, or excuse me, we can't just calculate the difference. So remember when we did our Foundations of Inferential Statistics z-test, we had our z-test, and within that z-test, we compared our sample mean to the pre-existing mean. And we did a subtraction problem, and then we said, okay, look, we can't just say, is there a difference or not? We acknowledged with the sampling distribution, there's always going to be a little bit of a difference. The question was, is there enough of a difference? And so to find if there was enough of a difference, we divided by something to kind of normalize that. And ultimately, it was our measure of error, or our measure of how different individuals are, so that we can see, okay, is this group difference way different than we would expect with just random variation, or is it about the same as we'd expect with random variation? So here we have to do the same thing. We have to compare to something else to establish if this variability between the group means is more than what we would expect to be there by chance. In ANOVA, what we do is we take the variability between the group means and compare it to the variability that isn't from between the group means. So pretty much we have variability from the differences between groups and variability that's not associated with the differences between groups. And those are the two variabilities that we compare. Ultimately, the variability between the groups looks at each group mean and essentially calculates the variance of it. The variability from not between the groups looks inside each group and calculates the variability or the variance within each group. So what's the variance from group 1? What's the variance from group 2? And kind of takes an average of all of those variances. And that's how we get this variability that's not associated with the group means. It's not associated with the group means because when we take the variance of the group 1, it's varying about group 1's mean. When we take the variance of group 2, it's varying about group 2's mean. So we're kind of ignoring the fact that they could have different means. We're ignoring that completely. We are just focused on how different are people within the groups. That sounds a little bit weird, but let's look at a picture, and I think this might help. So here's picture A, and let me tease ahead by showing you picture B. So we've got two situations here. In one case, and what I want you to note is that both of these situations, the three groups, each have the same respective means. Group 1 in picture A and B has the same mean. Group 2 in picture A and B has the same mean. And group 3 in picture A and B has the same mean. So we have the same means here for each of the groups in picture A and picture B. What we see, though, is that the variance between these dotted lines, that's the variance that we're studying to see, are these different than one another? And we can do a little variance calculation between these. We're going to compare this, to the movement within. And so that is, how spread out are each of the groups? What I think you can see in these two images is that when this is more spread out, this looks potentially reasonable, that kind of group 3 maybe in group 2 aren't that different, and group 1 and group 2 aren't that different. Like there's people in group 1 that are higher than the mean in group 2. There's people in group 2 that are lower than the mean than group 1. So like the spread is kind of masking the fact of the differences between the groups. That is, the variability between the groups is the same, but the variance within the groups is rather large. Picture B has a much smaller variance within the groups. That is, everybody's within their group is pretty tightly packed. So here we have a pretty small variability inside of each group, and that makes our comparisons of the group means pretty stark. It's pretty clear that group 1 and group 2 are different. There's absolutely no overlap here. So group 1 is definitely going to be smaller than group 2. Again, in this first picture, we have quite a bit of overlap. It makes it a little more difficult to discern. Is group 1 really different, or was it just the sample? In the second picture, picture B, we have something that's a little bit more clear, where group 3 is definitely higher than group 2. Group 2 is definitely higher than group 1. But again, the distinction didn't come from how different our group means was. Those stayed the same. The distinction came from how spread out our data was. All right, well, this has been our introduction to kind of the idea of ANOVA. In the next video, we're going to go on and jump into some of the theory.